let's make a new YouTube video. Haven't made one in a while, and I do have a topic here that would be interesting to discuss in general and also as a Python example. So let's so today I'm gonna show in my course CCPS 109 Computer Science 1 for the Chang school. So all the marking is such that we have a bunch of lab problems. So this document lists 109. So scrolling down the PDF document, so here we can see the table of contents, all the 109 problems, these days 111 because I put the 2 bonus problems, starting easy and then getting harder. So just from these titles you can get an idea what kind of questions there are. So students can choose freely a subset of up to 50. Of course they can do more, but A+ is the highest grade that I can give in Ryerson. So if you do 10 of these, get them to work with my automated tester during the semester. So you can do any problem at any time, so we don't have any kind of a weekly schedule. So just submit at the end of the semester. So this is all like very flexible and relaxed. So let's clicking like one just for example the words with the given shape. So we define, so we have many of these problems. I use the data file words sort. It got 300 something thousand English words in there, pretty obscure also. So here is a lab problem asking that they write the Python function. So all of these notice always give the signature of the Python function to copy paste and then explain what to do, and then after this this specification always try to be as unambiguous and concise as I can, and then put some jokes in there if I have room. So just this kind of searching problem that your functions given this giant word list and then this kind of shape. So like whether the step between the consecutive letters, like a C from O is higher, so +1, and ON is before O, so -1. So they always giving like this bunch of example arguments to also explain the problem. So going to the, here I have a Python, so I have the tester script open. So after I show you how this works, so we're gonna be reading parts of this tester script. So just to show that what is going on. So the labs 109. So this is the file that the students write all their functions. Of course, I'm not gonna show you mine in here because I got all the private solutions here. But so running this automated test, let's see what we show up in the console. So this automated tester, what it does, so reads the file labs 109 that contains all the student solutions, and then for tests each of these functions. So this automated tester for each of these functions that I specify, so I define a generator of pseudo-random test cases. So you can, each one is testing like 1,000 or such randomly generated test cases. So the automated tester for all the functions that you've written into the labs 109, so would run precisely those tests. So in my example, I got all of these 109 implemented, so 111 these days with the 2 bonus problems. So this automated tester also is friendly, that it executes the test in the order that your functions are physically in the source file. So then you always put the new file to the front, so it always gets tested first. So some of these tests are pretty heavy. So then taking I tried to make this like would be like a second or 2, so that then if the solution is like 10 times slower than that, so then there's some kind of inefficient repetition going on. But so these problems that they're all in a one PDF document, and so as this is running, so I guess we could look at the PDF document again. So here in the table of contents, like we said, so this start pretty straightforward, and somewhere on the second page, so it's like end of the first intro course, and then on the second and then in the third page we're getting like a pretty weird already, like I'm not expecting many first year students to do the with offer. So that's but all of this I try to make them like a fair and fun, and then we get to like the final bosses. So infinite Fibonacci word, I always have it I always keep it as a final boss. So over the years, I think I've had like 160 or something problems. So but I keep this fixed so that every new problem always has to earn its way in. So over semesters, so this collection, all the dead wood being cut out and all the inconsistencies. So this should be a pretty like a good. I don't think a student doing at least the first 50 problems is gonna encounter like anything very weird. But let's go back to the PyCharm. So we see that the tester script has finished running. So at the end it prints out how many of these functions pass the tests, and then so this is then gonna directly translate to the student grade in the course. So so a student starts with the baseline of 40 points, not quite enough for a passing grade in Ryerson. So every lab problem that you get to work and pass the test on your during the semester. Well, we can discuss the advantages of this system compared to the. But so each one of these is 1 point. Even the easy problems 1 point, and the final boss is 1 point. So you just you collect the points over the semester. So you start with the 40 points, and then you need 10 points to get 50, and 50 is the Ryerson passing mark D minus, and then so just over the grayscale. So if you make 50 problems, so 40 plus 50 is 90. So 90 is the A plus in Ryerson. So I can't give any higher marks. So I think the record for a semester for a student to do problems was 75, at least in my sections. I don't know, some other instructors also use this, so they may have different experiences. But of course, this is not any kind of speed run. But the advantage is that so in the course that design that we get a lot of variety of students. So from a whole bunch of backgrounds, some of course never programmed before, and others then done much. But in this scheme, like starting from day one, so anybody can just immediately fall into the to the place that is natural doing things. So total beginner. So first 4 weeks we just teach the basic Python and use the excellent coding bat for exercises for the first 4 weeks, like a training ground to get to the battle, like a boot camp. And then so after that, for the next 9 weeks, so students should be then working with this problem. So in the lectures, I teach all kinds of useful things that are gonna be useful in these problems in various ways, and then at the end of the course, so we can discuss all the big ideas, and then meanwhile, so students are finishing the labs that they do. But let's just go to this automated tester script. So this is how you use it. So you just from this GitHub that I have. Notice I had to check even how to record on a Mac because it's been such a while. But so here in my Python problems GitHub repo, so here we have all the files that we need. So students just clone, so download this, and then you can just working into labs 109 file. So I've given like as a freebie here, like the solution to the first problem. So then they can run the tester, and then know that it's working, and then start adding their own solutions into this file, and the data file word sorted. And then also, so how this automated tester works. So now this question, like so how do I verify that the student function is correct? So without releasing my own function as a like a comparison. So looking at the tester, so that's gonna be explained. So the tester for each problem generates a sequence of a pseudo randomly generated test cases. So they're gonna be the same for you when you run it in your machine and I run it on my machine. So we both get the exact same test cases, and then the file expected answers, this contains the expected answers for the test cases for each problem. The first 300 now, but then there is also a checksum calculation for the answers. So if your function's answers produce a different checksum than my function's answers, so then we know that our functions are somehow different, at least one answer was different. But that's a kind of passive aggressive, like a student tests a function and then the tester says that it doesn't work, but it doesn't say what's wrong. Like that's just a classic passive aggressive behavior. So we don't want that in here. So therefore, then after the first semester, I modified my tester that as it calculates the checksums from my private model answers, so it also at the same time writes the first 300 expected answers for each method. So then if there's a discrepancy between my private model solution and then the student function, so then probably it's gonna be revealed somewhere in the first 300 test cases. Otherwise, it's a really rare edge case situation. But in that matter, it's interesting in a different sense. So these all the files that are needed, and also for the replit users. So we make it so that the replit start with the reasonable settings with this. But so let's look at this automated tester. We can actually look at it here in the GitHub, get some bit more color and size in it. So let's read through the tester script. I'll explain the idea, what is going on, just and then when you get the idea, so then the individual details. So at the beginning of the script, of course, we got a whole bunch of imports here. There's nothing strange there for any Pythonista, but we're gonna be using lazy sequences a lot in here. So I do these lazy sequences during the course. I think it's module 7 or something like. So anybody who uses lazy sequences is quickly gonna fall in love with them. But so what do we have here? So some settings. So first the version that's gonna be also part of the expected answers. So to avoid the mismatch between different tester versions. Pseudo-random, we use the Python's standard library, the random, and that one is documented that it's the same everywhere, so it's whatever the Mersenne twister or whatever. So then we use also the same seed. Of course, any seed would work, but just to have something. Now, if I had a true fate, I would have made the seed to be 0 and been really cool. But so I don't want to change all the checksums, so that's what the fixed seed is gonna be. So then, so how many of these answers, when I'm recording, calculating the expected checksums from my private model solution, so how many of these answers are explicitly returned to the expected answers? So 300 should be enough to reveal most logic errors. So otherwise the file is gonna be ballooning. Now also, as when we see the test case generator, so of course the idea is that I generate the test cases like in a roughly like an order of the size. Like if a function to be tested takes a list of elements, so first a couple of a single element list, and then a couple of more 2-element list, and the 3, and so this way like a growing. So that the idea is that the first test case that whatever reveals the bug, so would hopefully be like as short as possible, not like some 1,000-element list. Start looking for the error there. So just trying to be helpful. So then some method functions take a much bigger test cases, like just to ensure that nobody's doing like some quadratic times linear technique when a single linear loop over the items would be fine. We use the name of the record file, and then for during the development, so that I can change the the test case generators create, so that I can delete that ignore the expected answers for a while. A couple of markers, so that the expected answer file is nothing but like a zip decompressed lines of text, and then these are not supposed to be appear like as expected answers ever, so that I can tell like where does the contents of the record file end for one function and start for the other. And then so this semester I also implemented the functionality that each test, the test for one function have to complete in this many seconds. So I tried to make all this that generate complete in 1 or 2 seconds, so giving like a factor of 5 in there. For like a student not optimizing as well as I do, but so of course, so that should be like enough like like a leeway there. But so like if all this, like if the test is gonna take like a minute to run, like you obviously have like some kind of super redundancy, like some quadratic time loop, semi loop when you're supposed to do things in just one linear pass. A couple of utility functions here. So when these functions return something, so some functions might return a Python dictionary as an answer. So now for the checksum calculation and such, it is extremely important that that the dictionary is like converted to text to the exact same way. So we have a utility function canonize that if the result is an instance of dictionary, so we turn it into a list of key value pairs and then sort with the Python sorting, so that everybody gets the same. So because otherwise, so this one actually interesting. So back in the day, so Python set and dictionary didn't guarantee anything about the iteration order. So when you iterate through the set or a dictionary, you get the elements in some order, and that may be different for you. I mean, but the Python 3.7 actually changed that when you iterate these sets and dicts, so then you are guaranteed to get the elements in the insertion order. But here I still have to canonize in 3.7 for the reason that when a student algorithm creates a dictionary of results, so that may be created the elements in a different order, so that cannot possibly affect the acceptance. So therefore I have to canonize all the results. Now then some functions, so this also useful addition as it turned out, some functions when they receive that the humongous word list, 300,000 English words, so now if we're spitting out an expected answer discrepancy, so the test case arguments, what was expected, what the student function actually did return different from a previous line. So now if the test case arguments includes that the entire word list, so we try not to flutter like that. That's just another version of passive aggressive behavior. I'd say that's, I guess, the malicious compliance as the kids call it. So it's just a utility function that when we have a list of arguments to emit on the console, so just like if it's too big, so then just print the list like the first 5 elements and the ellipses and the last 5, so just to keep it nice. Here I have a utility function that since I have my private solutions file and then I have a student file, so I can run like a student the test case like a log step for the student function and my function, and then like the counter discrepancies or just to find the first discrepancy. So sometimes like a student code could have a bug that is revealed only by like a really rare edge case that this has happened, and then another big source of discrepancies is accidentally using floating point operators. So then I, of course, because I hate the floating point, well, no, hate it, but so like I have a need here that everything has to be unambiguous for the checksums to work. So floating point imprecisions is something I cannot tolerate. So therefore, floating point is not used for anything in this level. Sometimes students unintentionally, like in Python. So well, if anybody who writes sqrt like is like not just wrong but doubly wrong. But sometimes like a test case has to be pretty big for the floating point imprecision calculation to come out. So things like that can happen, and then also like a really subtle optimization and logic errors have been discovered with this. But so let's first actually look at the one test case generator. So we were looking at that. What was the name of that problem that we were looking? I already forgot. But well, let's look at another one. Carry on Pythonista. So here's a problem: given 2 positive integers. If you add them like you were taught to add column-wise, like a question is how many times is there a carry? So like for example, if you take 1 and 1,000 zeros and subtract 1, 2, 3 power 4, 5, 6, so this is a number, and then you add it to this one, so result of course is this one, but then you notice that there's a carry in every column. So there isn't like a consecutive zero bunches anyway. But okay, here's a problem. So count carries. So let's see, how do I verify that the student solution is doing the right thing? So let's go to the tester, and okay, I realize I should do this in here. So count carries generator. So for each function, so I just always name the generator accordingly here in the tester. So as an argument, the pseudo random seed, and then we create the new local instance of the RNG with that seed. And then, so at this one, I also actually, like I keep preaching in the class that whenever you're repeating yourself, you're just doing things, well, not necessarily wrong, but you're not doing them the best way. So then I load all my generators. So because I want the, like these test cases, like I want the one element test case, two element test cases, three 4, so that I get like more test cases of a bigger length, because of course there's more combinations there. So I just been so n is like the current length, and then like doing like a pyramidal numbers, no triangular numbers. I always get those mixed up. So that maintain like a count, and then a goal. So n, the current length is 1, and current count is 0, and then the goal to get is 2, and then I generate 20,000 test cases for this particular problem. So A and B randomly chosen. The scale is determined by the current n, and then okay, looks like a random int. I wrote some kind of a this is a utility method that I wrote, so that with using this RNG produce a random number with this many digits with this percentage chance of I think choosing a new digit. So so that this one can create like numbers with the random digit repetitions for other problems. For then we're gonna be yielding. So actually, this is yielding 60,000 test cases. So 3 times 20,000. So if your function produces the same answer for all of those than mine, so the same checksum. So I'm willing to bet my life that like our functions do the exact same thing. So this logic that for every time we generate, so increment the count, and if this makes the count to equal goal, so then we increment the n 1 notch forward, count goes back to 0, and then the new goal is updated somehow. So here, I'm obviously creating like test cases now in a logarithmic scale. So the goal that has to be reached for the next increase always doubles. So we can put different formulas here in the goal and the n increment to produce like a different variations of the pyramidal series. And then I realized that actually yesterday that I've been doing this so much that now here in the new version. So let's go to this. I have a new. So just take the logic of the pyramid series and turn it into a generator. I already edited a couple of test case generators, so it removes for about 5 lines of code from each. But so this I will use this at some point in the future to save away 500 lines from this test. So it's gonna be one of my most productive days. But each generator, so it's written as a Python generator. So all these are lazy sequences. So generator just runs some and yields the values. So these are lazy sequences. So I got a lazy sequence object for every function that I recognize. So scrolling down again, so over all these generators, so I got all this arithmetic progression generator and cookie generator and eliminate neighbors generators, and sometimes just using all the permutations is gonna reveal a whole bunch of logic errors. So why not? So scrolling down past all these generators. So I have so many. So now we have a list of test cases. So this is like every test case is a triple. So the name of the student function to test. So when this script is reading to the student script, so then it looks for the function names and sees if there is a corresponding test case for them. And then the lazy sequence object. So notice this for a Python lazy sequence. so calling that lazy sequence as a function. So this just creates the lazy sequence object, but it hasn't started running yet. So we're only gonna be asking test cases for the lazy sequences for which we have the corresponding student function written. So like some generator that reads the entire word list. So it's not gonna even take any memory until we actually need it. So one hooray for laziness here. So in this list, so I have a whole like for each, and so then the generator and then the expected checksum. That this is calculated from my private solution. So this script has a mode that if the expected solutions file doesn't exist and we wanna use it, so then do in the recording mode. So then just run. So run all the testers for this my private model solution, and then just whatever my model solution function answers is the only correct answer. So it's return to the expected answers file. So in this list, so here we also notice that so I didn't do this like from the beginning. So like the first 20 problems that were removed, so they don't even have a tombstone in here. So somewhere in the 2019 when I first created this. So all these problems that existed back in the day, so they've been replaced with the much better problems. So then all kinds of student issues that there like some problem if it generated like 1/3 of the issues in a semester. So that problem was pretty much the first in the chopping block. So then try to make like a smooth and mellow problems that don't cause like all kinds of ambiguities. Okay, so the list of this kind of triples, so I define in the tester. So let's go. Eventually, I'm learning the Mac keyboard shortcuts. So where are we going? So test one function. So what is going on in here? So you're given, this is the function object for the student function. So this script is just gonna import the student script, and so then we have all the function objects there. The script is also reading the student solution as a text, so both. So we get the best of both worlds. So yay Python. So like in Java or something, would you ever even do anything like that? The test case sequence. So what is it? It's just a sequence. Now we know that it's gonna be a lazy sequence, but if it was like an explicit list, then absolutely nothing would change. But the lazy sequences take a lot less memory, so I much prefer them. The expected answers for this particular function are we recording, and then known. I forgot what it was. It's gonna come up. So we're gonna be so also notice I like the F strings. I teach my students F strings. So using those like a C style modulos and such. So only thing I heard about the F strings that they're too late. Like it should be like F string is the default, like in modern languages. And then if you don't want the F string, so then you gotta put like a R in here, like a row that say that now you don't want it. Like we wish, like a Swift, for example, is much better this way. So if we're recording, so then print the information to the text file, so using this function prefix and the function name, and then so if the known is given, so okay, hold on. Oh no, sorry, expected was the checksum. Sorry, yeah, my bad. So this is the I should name this properly, but good thing we got refactoring. Expected was a checksum, and known was actually the expected answer. So okay, clearly there is a renaming. So this is now the classic rubber duck debugging. So I'm using all my viewers as a rubber duck. So I'm just rambling here. So create the so ask this what is the recorded answers. I use the word recorded back in there. So things evolve. So the checksum generator. So this doesn't really need to be cryptographic, but Python has the SHA-256 in standard library. So when the start time of the test, so once they get a timeout, so we can now forcefully terminate, and so then for the finish up, so whether the student function has crashed, so initially hasn't, and then so far so good, it's still good. So then looping to the test cases, and again it's my personal mission to eliminate every Python loop in the world for I in range of length of something, like anybody who writes that. So like just automatically turn it into enumerate. Like this works for lazy sequences. The way that you try to do it doesn't work for lazy sequences. So eliminate like Python enumerate, use that one. Like there's nothing to it. Okay, so we get like the position and the individual test case. Now really brave souls take away this parentheses, but I'm too much of a the Python tuple syntax of just a comma. Like I know how it works, but I just can't like accept that it works. Same in Mathematica. I cannot, like in the when you make a anonymous function with the ampersand, like I always put the parentheses around it. I know I don't need to. Real Mathematica people don't do that, but also then the test case, so the generator gives a tuple of arguments. Notice in Python how lovely it is that you can like blow up a tuple into like a function arguments, and it works for all the argument tuple lengths 1, 0, 1, 2, 3, whatever. So I don't need to write like a different function to test one parameter function and test a two parameter. Like it's all the same in Python. How lovely. So so if there is any kind of crash in your student function, so crash is never the correct answer in here. So then we just terminate the test and print so crash at the test case which number and what happens. So I guess I should also print I realize I should print the test case arguments also. Good. A lot of things for the new version coming up in the rubber duck debugging. So if the result, so we just canonize it and then convert it to string and then update the checksum. So Python strings, so we can encode them to Unicode. So this encoding is standard. I don't use any weird Unicode stuff, so that might affect it. So far so good. Nobody's come up with the discrepancy. So if we're in the recording mode, so then we just print the result to the whatever's the record file, and so then I also keep track like how many characters go to the record of each function. Like if a function takes like 200 kilobytes of a record, so I think the function output needs to be simplified somewhat. So then if we reach the recorded enough, so then we don't even run the rest of the test cases, because I believe that my private model, my private model solution is by definition correct. So when recording, so there is nothing to do. So then, so if we're using the record and this function as a known answer, and we're still so if we're using a record and we're still in the limit that there is a recorded answer, that this test must be redundant. Ask what the answer should be, and then if the correct answer, so if the return answer is different than it should be, so then we treat it as a crash, like giving the wrong answer is a crash. Print out the discrepancy report for the students, so the test case arguments what was expected and what the function actually returns, so can start the debugging from there. I try to make the test case generator so that you get hopefully as short a test case argument for debugging. The total time, so as the current time and whatever was the start time. So if once the total time is more than the cutoff, so then we also treat it as a crash with the different message. And then, so at the end, so we done this for all the test cases generated by the test case generator. Your function returned the answer. We updated the checksum and verified that your answer were the same as expected. So then in the end, so if we're not recording, so then enforce the time. Ask the checksum calculator. So what is the checksum of the data that the answer that you received? And then, so if the expected checksum is not given, so this for my development purposes, so this one prints me the checksum. I'm not sure why I do only the first 50 of the 64 characters. That's another like one of those, that they're like, why do you always cut the fish in half before you put it in the oven? So this might be one of those spirited stories. And then, so if you're not crashed, and then your so this the digest. So digest we ask the first as many were expecting, so 50, so is what expected. So that's this is not a line that you wanna see. So success, and then what was the total time. Otherwise, so crashed return -1, and that, so -1 means that the function failed, but the testing goes on. There's more functions to test, and then any positive number, assuming that the time cannot become negative, so then it means that it was a success. Now let's so just to wrap up this video. So we're just looking at this. So I'm reading so your student solutions as a text, and just the one line at the time. So again, notice I'm using enumerate instead of keeping track of the count myself. So then if the current line, so is start from, so is a def and a space. So okay, this looks like a function definition to me, and there is no cost if I'm occasionally wrong, so don't care. So I asked the line, like what is the name of the function that is being defined, and then just as a cost, again, cost me nothing, but I'm just such a nice guy that does a service for a student. So some student might have editing a function that the same works at the top, but actually they have another like a version of, in Python, if you do multiple definitions, the last one is the one that stands. So like this warning that your file has a multiple definition, so the results might not be what you're expecting. So that you're at least aware of this. So then, so we build up a dictionary of all the functions that the students implemented, and then which line they're at. So then now we can take the list of the test cases that you just saw so that repose of the function generator expected. So we're gonna sort that list now, so that we sort each of these triples by its so where by its line number in the source code. So then the functions are tested in the order that they appear in the file. So this just implemented, okay, I think was after the first semester, just as a convenience. So this course that I'm teaching, so it's after this semester, it's exactly 20 years. So 17 years in Java, that was a whole bunch of development there, and now 3 years in Python. And so when they announced that in the Ryerson Computer Science Day School, switching to Python, I was first skeptical, but then I essentially wrote this automated tester for myself, like in an hour. So I was completely sold at the time. So why didn't we change to Python 10 years ago? So I can only wish. Okay, so test all functions. This is the main activity of this automated tester. So if we're in the recording mode, so inform of this, and then we take your this one produces the test, the individual test, so consisting of the student function name, test case generator, and the expected checksum. So is this function name implemented in the student solutions? So if it's not, so no biggie. So just continue. Python uses exceptions as a control structure. So for a Javaist, this looks weird, but I'm learning to accept this. So how many functions? Test one at the time. So if the result again is non-negative, so that was one success. So then just count how many of the total functions work. So the length of the test suite list is how many functions we recognize. So I keep it now at fixed 109 plus certain bonus problems that I'll be adding very slowly whenever the situation emerges. But so whenever new problems are created, so they always have to displace an older, less good problem. So this just increases the quality here over time. Now some utility functions, so to finish this off, so scale random, so this basically produces like a sequence of somewhat exponentially growing numbers. No, not really perfect like statistical accuracy, but like just that I get a pseudo-random series of exponentially growing numbers, and then with the scale and the skip I can adjust the speed that the exponential is growing. So I get like if I want test cases of for a function, I want test cases from all scales. I want the small ones, but then I want like even 1,000-digit test cases. So I can then get the pseudo-random integers from here. And here's another one. So so if you want to create an n-digit number, so start the current number with the single digit. And okay, looks like we're actually, I realized we're creating an n+1 digit number. So I mean, it's the same matter here, but let's just be accurate. So the loop, so n times, so shifting the current, car is the current digit, and then r is the random integer. I don't know why I'm using r for integer here. So adding a new digit to the n, so you multiply by 10 and then add the new digit, and then so if we roll a 100-sided dice, and if that's less than the probability, so then we update the current. So with adjusting the probability, so you can like how many long runs of a same digit you get. So you might get like a more interesting test cases that way. Random string is too trivial to explain, and now we have the test case generators. Yeah, so with the advantages of this kind of a scheme where student over the semester in their own time and in their own completely choice of order of things. So this has many advantages that I would claim that compared to the way that the intro programming courses run, so that you have a weekly labs and submit to TA, and then TA responds whether it's accepted or not, and then you gather for the midterm and final. So you gotta switch the mental mode, what is the professor gonna be asking. So none of that here. So all the grading in my course, so it is just this graded lab problem. So if you do, so if you can think, if it makes you feel better, so let's say you do 40, so that 20 of them are like the weekly labs, like a 2 per week, and then it's like a take-home midterm, and then is a take-home final. Like if that makes you feel better in this globalized Zoom age, what is the difference between a lecture and lab these days? Like there is no difference. So the students coming from different backgrounds, so they can, so students who already coded before, they don't need to wait for the week 5 or 6 that they get the first problem that they have to think about anything. So they can immediately hit here, and then the students who take let's say one Python course in high school, I can do this. Well, those students they can start with the also doing this graded labs, and they ask me is it for real, sis, that all I do this? Yeah, for real, I'm not making this up, why don't you believe me? So once that hurdle is passed, so those guys, so they start with but then they'll soon learn they aren't quite as skilled as they thought that they are, and they the bullshit solutions that flew in the high school Python, I guarantee that they don't fly against my automated testers. So I always put my thumb on a scale to guide the randomness. So enough randomness. So if I blast a shotgun at you, you're not gonna be like a Neo and dodging every single shotgun pellet, no matter what you do. So and then students who never programmed before. So then what I do with such a students. Again, don't even need to start here, but we go to the excellent coding bat site. And so this one, I'm sure a lot of people know. So I fell in love with the Java when I found it, and now of course in Python. So for the first 4 weeks, so what is for example warm up and then what so for the week 1, and then the week 2 is the if else, how to do conditions, so we can do logic 1, and then the 3rd week the list and other sequences, and the 4th week the for loop. So that's all you need to do all the labs, all the language, the basic the tools of the trade. So what do you need? You need some kind of way to express data, some kind of arithmetic. You need a 2-way decisions and a way to repeat, and after that that's all the language you need. So you can enter the phrase. So you can start doing the graded labs, and so after you learn the tools of the trade with a simple problems given an array of ints, return true if 6 appears either as a first. So this kind of problems coding, but is awesome. So what do we nums 0 equals 6 or nums -1 equals 6. Yeah, so notice how coding bat so shows a bunch of test cases, so the students learns that like a function it's gonna work for all the test cases, not just some of them. Like if you make a classic mistake of using and in place of or, so you notice some test cases still work correctly. So then this red was like 1, 2, 6 was supposed to be true, but the return false. So like this like right away from day one, like learn the idea of testing and such. So once the students learn the basic language in the core coding batch, so then the skip to the graded labs is then hopefully not too big. So every problem is just one function. Now what if something's so big that it needs 2 functions, data and a pass? Well, that's the next course, CCPS 209, object-oriented programming in Java. So in this first course, so there's no object-oriented programming. Well, the last lecture I do teach it, but like as a segue to this, but like none of this needs anything fancy. This is like a like a lot of material like that you read that has a problems, has a couple of good problems and then a whole bunch of fillers. So I thought like what if I just collected all the good problems and put them all together? Like what if there was no like a stupid problem? Like only put like a good and fun and educational problems. So based on the student feedback, so this approach seems to be working. Like any subset of 50 that any student does, like I got no problem like betting heavily that students understands Python and coding really well. So I don't even care like which problems a student like this is like I'm like a gym owner. Like there's 109 different machines and weights. So as long as you're using one of them and using them according to the right form, so like what do I care? Like the same thing here. Like if a student has a fractal or a recommend items, like either one, like you're good, like you learn the stuff. So this is like well, this is getting a bit long. So how big this gonna become? So I think I'm gonna end the video, but hopefully this gives you like a idea like around the course, like some of the whole bunch of like advantages over the years, like for students, that you don't need to make the mental shift to the midterm and final, like the things that you know, just afraid like how is the prof gonna ask them, like no such thing here, like all my these problems are right here, like you know exactly what I'm asking, you got no uncertainty, like that stress is like a gun, like so that you don't even need to distinguish between labs and test and final, like it's all the same thing anyway in the modern world. Like I don't care like what time you're gonna like do these 50 labs, like as long as you do them. So this humongous flexibility, like especially like for adult students with real lives and real jobs. So I just try to be of service. Okay, but let's so end this video now, and hopefully so you get the inspiration to. So all this is free to use and copy and GPL licensed. So and if anybody uses this in their teaching, so let me know. So I need the feedback. So good something.